In the 1670s, Isaac Newton discovered that white light is a mixture of all the colors of a rainbow. He named this display of color after the Latin word phantom. Newton did not know at the time that he had missed one of the most important discoveries in the research of light.
"150 years after Newton's discoveries, William Herschel was exploring the night skies with the largest telescope of his time. While testing the relationship between temperature and color of light, he discovered that red light is warmer than blue light. This led to the discovery of a new kind of light, infrared light.
While Herschel was discovering a new kind of light, at the same time Joseph von Fraunhofer was working with a royal mirror maker in England at 11 years old. By the time he was 27, he had become the world's leading designer of lenses. Fraunhofer magnified the sunlight spectrum with a telescope and saw dark vertical lines within.
In glass, violet light, which has the shortest wavelength humans can observe, slows down more than red light, which has the longest wavelength humans can observe. The changes in speed spreads the white light colors apart, which gives the spectrum we can see after passing white light through a prism.
In 1802, a British chemist, William Hyde Wollaston, was the first person to notice dark lines in the solar spectrum. 12 years later, Fraunhofer independently rediscovered the absorption lines and began to systematically study them. In his work, he mapped over 570 spectral lines and categorized them by their principal features.
Spectral lines are the dark gaps seen on the electromagnetic spectrum. In an atom, the electron does not exist between orbitals. It disappears from one, stops existing, and then reappears in another orbital. The electron makes quantum leaps going up or down from orbital to orbital. The upward leaps are caused by an atom absorbing light, but we have no idea what causes the downward leaps.
Currently, modern scientists have no idea what causes the quantum leap downwards. However, the downward leap always produces a light emission whose color matches the energy difference between the orbitals. When the electron drops to a lower orbit, the light wave it emits scatters and most of the light doesn't reach us, resulting in a dark gap in the spectrum.
Cannon categorized over 250,000 stars at Harvard with a team of women scientists. At the time, Harvard was a man's world, but an astronomer, Edward Charles Pickering, assembled a team of women to map and classify the stars with Cannon as their leader. Henrietta Swan Leavitt was a key member of this team. She led to the discovery on how to calculate the distances to the stars and how to measure the size of our universe.
Cecilia Payne grew up in London in the 1900s when women weren't allowed to pursue careers in scientific fields. She moved to the US to pursue her dreams of becoming an astronomer. After her application was accepted at Harvard, she joined Cannon's team, where Cannon taught Payne everything she had learned about star spectra. Payne used this knowledge and all of Cannon's observations to identify the chemical compositions of each star, and also categorize each star by the temperature scale.
Spectral lines represent how when a star gives off light, not all of it escapes from the star's atmosphere because some of it is absorbed by the floating elements and jumps electrons up in energy levels. Bunsen and Kirchhoff noticed that some of the emission spectrum from the elements they had been heating up matched the absorption spectrum of previously recorded stars. They used an optical spectrometer to produce and measure the properties of spectral lines.
The electromagnetic spectrum was used in determining the temperatures of the suns and their compositions. In the 1860s, William and Margaret Huggins used the non-relativistic Doppler shift equation on the spectrums of the stars to determine their axial speed. And Balmer discovered the 4 visible lines of hydrogen, which led to the creation of the Rydberg formula.
When we look at a star with a spectroscope, we can see the dark lines from all the elements in its atmosphere. The discovery made by Cecilia Payne is still used by scientists to categorize the stars according to their temperature and their chemical composition. In the early 20th century, spectroscopy research contributed significantly to the development of quantum mechanics. Based on the pattern of lines, astronomers can determine the distance and movements of stars and even entire galaxies.
Here are some famous quotes about the electromagnetic spectrum and spectroscopy. In conclusion, since Fraunhofer originally charted 570 spectral lines, today there are around 25,000 known absorption lines in the solar spectrum. Most of what we know about the universe has almost been completely obtained by analyzing the spectrum of light from stars. We owe this to Joseph von Fraunhofer due to his pioneering work with the electromagnetic spectrum and spectroscopy. Using spectroscopy, we can obtain information on kind of source, radial velocity, composition, and temperature from positions and intensities of the spectral lines. Thanks for watching.